Hello, everyone. The topic for our presentation is karma economies. In this, we look forward for a fair and efficient approach to allocate price resources. So, we are a group of six in which we are the members are Shikha, Soni, Vanshika, Gupta, myself, Aneerban, Chowdhury, Anugrih, and Disha. So, moving forward. In this paper, we are addressing the challenges of public resource allocation. The two major challenges that we face right now is that number one, we have very limited resources. Considering an example in which we are considering resources like highway and parking spaces. So there are very limited resources over here. So this is our number one challenge. The second challenge that we face is the diverse needs. Every individual has their own need. Suppose, for example, an individual who lives in a city area has mostly needs of parking spaces, whereas an individual who has to travel across places require a high speed travel on highways. So these are the two challenges that we'll be considering here. Moving forward, here we are introducing the karma economies, in which three major aspects we have considered. Number one is the karma credits. In the karma credits, we give each individual receives some karma credits for different resources. Like in this case, we are considering two resources, highway karma and parking karma. Secondly comes the bidding for resources. So using their karma credits, each individual can bid on the resource that they feel is more suitable as per their requirement. Third one is redistribution. Now, redistribution ensures the efficiency and fairness amongst the resources that is being distributed to the individual. Moving forward, the importance of karma economics. Like I stated earlier, the redistribution aspect ensures the fairness. Secondly, efficiency has been ensured by if people are bidding according to their needs, efficient resource allocation can be done. Third is the self-contained. Self-contained comes in picture when karma system operates independently using the traditional money system, uh, which promotes fairness as well as inclusivity. Now, the key design considerations that we have taken in here is coupled resources, redistribution strategies, and exchange rate. Coupled resources is in the paper, it focuses on situations where resources are linked. For example, if one individual is more inclined toward parking allocation, it would somehow impact towards his highway allocation. Redistribution strategies. So in karma economies, what happen is redistribution to all the reusers is done time and again. And exchange rates, so users can exchange karmas between different resources, and this is how the exchange rates work. To tell more detail about this, I would like to hand over this to my teammate Shikha.
Thanks, Vanshika. Uh, going ahead, I'm going to discuss what the paper talks about how the karma based resource allocation system works for two interconnected resources, that is, highway lanes and parking spots. So, understanding these two resources, so in the above, we can see there is one resource which is highway, and it has two lanes. One is the priority lane, and another one is the general purpose lane. And the next one is the R2, which is parking, and it also has a parking priority parking and the general purpose parking. So to access this priority lane, driver bids with karma points B. So B is the karma point bidded by the driver, and if it belongs to the maximum bids, then they are going to get a priority resource, and otherwise they are going to general purpose resource. So I'm talking here both about the highway and the parking. uh, Now we also see the green arrows among these two resources. So what does it signify? It signifies like the choice of one resource affects the other. So suppose if driver chooses higher bids for priority lane, then they have fewer karma points left for priority parking. And if they choose lower bids for priority lane, then they will have the higher karma points left for priority parking. So this is how these resources are getting affected, and this creates the trade-off, like which is strategically chosen and encourages fair distribution over time. Next, we are going to discuss about the resource urgency Markov chain, where we discuss about the urgency dynamics. So here in this, they have taken this example where we have two types of resources. One is suburb type S, and another one is type C. Here we are also defining the types of urgencies, which is U equals to 0, U equals to 1, and U equals to 9. 0 means there is no urgency, that is no need of resources to the users, or 1 means there is moderate need of resources, and 9 means there is a very high need or strong need of resources. So in every scenario, how the bidding will work or how the user will bid, like for user or no urgency case, in this case, user will not actively compete for the resource, so they might not bid at all, or they will bid very minimally. In the moderate case, they will bid for the resource, but they will not bid aggressively, because they are willing to accept the delay if no priority access is provided to them. But when we talk about the high urgencies, the users bid very aggressively for the priority access. So we are going to discuss about the behavior of the users in all of these cases. So when we talk about S users, so they need both resources daily, both as in highway and parking, as we can see. And their urgency level may vary as their urgency is drawn at the start of the day. Like in the figure, it shows that there is 75% chance that user will have moderate urgency at the start of the day. And as users are always active in both resources, and but their urgency level, they are varying, and they must bid for both highway and parking resource duly using their karma points. But when I talk about C resources, we can see that they do not have any urgency for the highways. They definitely need the parking, and for parking, they have moderate and high urgency at the start of the day, and they do not have any urgency for the highway. So they will always bid for the parking, but they will not bid for the. I mean, they will bid minimally for the highway, and how it affects their karma. So karma which they are using. So when we talk about the heterogeneity, like they have different needs and different urgency levels. We talk about the resource coupling, like how user transition between highway and parking resources and their urgency state, which affects the bidding strategies. And for example, like S can use their karma across both resources, while type C can focus more on the parking. What is the impact that we can discuss is, like urgency states influence how users bid for resource. Like for u equals to 9 leads, when this is the case, then it leads to higher bids for priority access. But when u equals to 0, there can be no bid at all. So this affects how karma is redistributed and exchanged between resources. Paper also says about how karma distribution exchange rates affect resource allocation. Uh, Moving to next slide. So it discusses how resource urgency transitions. So here we are seeing two particular equations, and in equation one, when we talk about, uh, basically these are the part of resource urgency Markov chain equations, which describes how level in evolves as the users move between different resources. So when we talk about the first equation, it basically describes transition probabilities from moving current resource to next resource on the same day. And the probabilities of all these resources should be equal to 1. So the first equation signifies it models the sequential nature of user of the resource use, and it also ensures that the Markov chain is well defined. Uh, and the second equation, it describes the transition probabilities for moving from the last resource on the current to the resource. So this model defines the daily cycle of the resource use. So this ensures Markov chain is cyclic and that user restart the sequence of the resource each day. Next, I'm going to hand over to Diksha.
Yeah, hi. Now coming towards the priority access, suppose there is two lanes, express lanes and regular lanes. A highway has express lanes for those who pay extra bit and free but slow general lanes. So how priority works? If you pay a higher bid, you will get a higher chance of using the express lane. If too many people bid high, some still have to use regular lanes due to limited space. So higher bid increase access to priority resources, but congestion comes into a role. So congestion plays an important role. So moving towards a congestion delay, so this equation calculates the delay users experience if they don't get high priority access. So suppose there is a huge traffic, so it will impact congestion delay impacting priority access. So many cars try to use the express lane by bidding high or paying a toll. However, the express lane has limited space, so not everyone who paid can enter immediately. Some cars, despite paying, still experience delays because too many people are competing for priority. So the regular lane is even slower due to increased congestion. So importance is it captures the cost of congestion, which affects user decision on how much karma to bid. Now coming towards the average payment for redistribution. Suppose on a toll highway, driver pays a bid to use express lanes. The collected bid is used to maintain roads or improve public transport. So how redistribution concept will work? Suppose some drivers pay high tolls for priority access. The total money collected is averaged and used for road maintenance or subsidies for public transport. This ensures fairness. Even those who don't use express lanes benefit from the tolls paid. Now, coming towards the redistribution rules. So, there are two ways to redistribute to all and redistribution to active. Suppose consider a mall parking with a premium and general spots. So, money from premium parking reduces cost for general parking users, but only those who paid for parking receive rewards like discount or priority next time. So, this system decides whether to distribute karma to everyone or only those who contributed. Now I'm handing towards, now further will be explained by Anugrih.
Yeah. So, Aneerban here. I would be taking up the Nash
Sorry,
equilibrium
Anugrih.
part. Yeah, no issues. So, the point of Nash equilibrium in the paper is about so equilibrium is something wherein two things are equal or in an equal state. So, Nash equilibrium is a situation wherein no player can improve their outcome by changing their strategy. So, if the game is going on and someone changes the strategy, provided that no other person is also changing their strategy, there would be no benefit to the person. This is a classical example is present in prisoner's dilemma, which we discuss in the class as well, wherein there are two suspects and they if they both remain silent they would get the less punishment. If they both suspect each other or both confess about each other, then both will get higher punishment. If one does and if other doesn't, then it would be a moderate punishment sort of a case. So in this it feels the best case would be to not confess, but ideally if one takes advantage of it, it would be problem to the other. So ideally, the Nash equilibrium is a situation wherein they both confess and get the maximum punishment. So coming on to the next slide. So what is stationary Nash equilibrium in the karma economy? It is called as SNE. So SNE is a state wherein the distribution of user states in which is the urgency and the karma remain stable over the time, and no user will be able to improve their payoff, which is a long term payoff, by changing their strategy. So the existence of SNE is by making the equilibrium in the DPGs, that is the dynamic population games, wherein a large population of players interact over the time. And the SNE is calculated over a evolutionary dynamics inspired algorithm to numerically compute the SNE. Going on to the next slide, we see the importance of SNE in the karma economy model by three major points, which is your predictive behavior, evaluating the design, and fairness and efficiency. So, the predictive behavior is something the how users will behave in the karma system when they are acting rationally and trying to maximize their own welfare by not bidding or not changing their strategy to harm others. The evaluating design would be to find which person or which strategy would be the better, which would give better outcome in terms of fairness and efficiency. And the SNE here will make the system stable and will ensure that no one gets the incentive by changing their strategy. Now, the Nash welfare function is a equation to find the social welfare, and it calculates the relative improvement in the welfare compared to the benchmark set. That is no karma system. When there is no karma system, what would be the what would be the welfare? And while using the karma system, what would be the improvement? What would be the improvement in the welfare? It also avoids comparing payoffs between the users directly, making it more fair. And it is important because it evaluates the overall fairness and efficiency of the karma system. Now I hand over to Anugrih for the conclusion and summary part.
Yeah, hi, Anugrih here. So see, this paper, it does not consider various factors, like it does not consider the urgency of the users and the preferences that they have. That is why it makes it more difficult for a one size fits all distribution rule. And there are other drawbacks also, like people, what they can do is on purpose, they can stop bidding by accumulating more karma points. So in that way, this is not a good option. Like this is a challenge here. And moving to the next slide, the conclusion part. Yeah, so this paper, what we concluded here is the one-to-one mechanism, the uniform distribution of karma. So irrespective of people, those who have bid and those who have not bid, the karma points are distributed uniformly. This is the best way, and having a unit exchange rate for both the resources, for highway lanes and the parking. Same exchange rate is working fine, which is giving us the maximum social welfare for all the customers. Yeah, so that's it from our side. Thanks.